The likelihood of rapid intensification is promoted whenever the initial depression is stronger or whenever we rotate it in the clockwise direction. All right, so with the weather forecast, and this is really the part that I must admit we really do not control very well. Okay, WRF gives the user the possibility of injecting stochastic forcing into the dynamics. This is the so-called SKEBS, stochastic backscatter perturbation. The stochastic backscatter perturbation take place everywhere. Okay, they're really minute, but they perturb the environment. All right, and we wanted to see whether we could tell, the differences between our initial conditions perturbations and the stochastic perturbation as to what happens. And the first thing that you see, okay, is that if we run only initial conditions perturbations, then the storm tracks are really not changing much. These are the red curves. Whereas with stochastic backscatter, when you force the entire environment, even though we're perturbing the environment at things that are really minute, think of them as almost round off, okay? Because of the instability of the environment, okay, or those environmental conditions at the time of the birth of the hurricane, there is quite a bit of deviations in the storm tracks, okay? The stochastic ensembles, and this is, I'm fixing the initial conditions and I'm just seeing what happens, both to the maximum wind with time and the minimum sea level pressure with time, okay? Then I do get envelopes that are similar to those that I would get by initial condition perturbations, which is good. At least these are of the same order of magnitude, and we can try and decipher which is which, okay? Unfortunately, if I try to do both things at the same time, okay, and based on the first part of our study, we learned that the initial storm or initial depression amplitude and its rotation are really the dominant parameters that affect minimum sea level pressure and maximum speed. So we ignored the other two, we ignored the unimportant parameter and simply sampled these, and at each one of these samples, I ran multiple calculations, so fixed initial conditions, but simply run stochastic forcing, all right? And what you see is at each one of those initial conditions, what is going to happen, all right? And in some cases, there is a little bit of a deviation of the storm track, but in other cases, the deviations are severe, okay? And at least in this setting, trying to do a variance decomposition and trying to decompose effect, even though we have the tools to do it, we may not have the sample size to do it, but we do have the tools to distinguish in a rational and systematic way between parameter uncertainty and stochastic forcing uncertainty, because I'm thinking of these as different samples, because every time I pick them, I'm changing the seed of my perturbations. Okay, the situation is quite difficult, and they're quite difficult because I really do not want to compare the wind speed, the maximum wind speed of a hurricane here with the maximum wind speed of a hurricane that is there. Okay, an additional complication is that the atmosphere calculation, when the environment itself is that unstable, okay, unlike HICOM, where the developers have spent an inordinate amount of time to ensure that the parallel applications of HICOM on serial and parallel are the same. In WRF, unfortunately, they're not repeatable. Okay, at least when the conditions of the environment are that unstable. Meaning, even if I don't have stochastic forcing, if I run WRF on Monday morning I get an answer. If I run it on Monday afternoon, I may get another answer, depending on how many processors are used, or if it's the same, even if it is the same partition, depending on how busy certain processors are because of MapReduce, essentially because of MapReduce operations. So stochasticity, that's already been mentioned, okay. A, the calculations are susceptible to round off, and B, they are also susceptible to parallelism because they are susceptible to round off, especially when the conditions, the atmospheric conditions are that unstable. That, I must say, I really don't have a ready answer for. If we didn't have at least the lack of repeatability, we could at least try to learn something about stochasticity in a situation where we don't have major impact on the storm track. But the lack of repeatability, at least, is really a problem for us, because it really makes meaningless the fact that I'm fixing some parameters, I'm fixing the seeds of my random forcing, but if the parallel computing environment is acting as its own random number generator, then this is really something that at this stage I really don't have the tools to start addressing, and that let me control that, barring making sure that the atmosphere simulator, whether I run it in serial mode or in parallel mode, regardless of how they are, the reduce operation are always done in the same way. But that is really not at our fingertips yet. Okay, so this is the summary, at least, of that rapid intensification study and the initial depression conditions. We obviously learned quite a bit about uncertainty in this couple system setting. We learned quite a bit about what properties of the initial depression will affect rapid intensification or dominate the variability or the likelihood of rapid intensification. There are some challenges that are associated with trying to decompose variances whenever we have multiple sources, whenever we have a parametric source of uncertainty and either inherent or user-defined stochasticity. But this is something that is ongoing work, and hopefully by the next time we come back to Japan, we would have figured something about it. So thank you very much for your attention.
Thank you very much. Any questions or comments?
Yes. Yep.
So are you working with the people collecting the data, the players, or do you think it's
I am working with the people who are designing data, but not in an atmosphere setting. I'm working with people who are designing shock tube experiments and rapid compression machine experiments for the purpose of calibrating chemistry parameters, if you want to think of them as parameters that, even though we're interested in hydrocarbon, but they're similar to what you have in atmospheric chemistry. And yes, we are actually designing experiments ahead of time, and we are using actually the Bayesian framework. Actually, this is really the most interesting things where many light bulbs have opened, not only inside here, but in people who are doing the experiments. Anybody here doing experiments? Okay, so I love experimental work, but at least I used to be doing experiments in a previous life. Actually, I used to be running factory, and much the same way that every piece of computed information you really need to analyze, it's really more so on the experimental part. The hard thing with the experiments is what experimentalists typically think their uncertainties are. And in the case of at least shock tube experiments, the laser calibration were beautiful. I mean, it's really mind-boggling physics. The experiment was done in a fantastic way. The laser signals are great. Okay, what you actually see, which is a voltage versus time, and it has so little noise. But then it was fed into an Excel sheet, and there goes your number. And the sins that have happened in that Excel sheet, which is an optimization, very much variational, which ignored the nuisance parameters and destroyed all the correlation between the parameters that it was trying to inform, is really disaster. I mean, the experiment may have cost $1 million, may have generated information, data that is potentially worth $1 million, but the way that the data was converted into quote-unquote information essentially butchered at 50% of the value. So luckily for that, in that collaborations, we've elevated each other. I mean, we've beaten each other so many times that at least the people who are doing the experiments are keeping the raw data. Because I start with the Bayesian machinery from the raw data. I mean, look, this is what you're doing when you're doing analysis. Exactly that. Except what's in the Excel sheet, you don't have a Hessian, and you don't have a nuisance parameter, and you forget about the correlation that is in the adjoint. If all I report is the map point, I destroyed maybe 90% of the value. Because on us, if they're really quite correlated, this is a much easier problem than say they vary in that range, which is the classical sin. You're trying to infer a straight line, and if you report A and B with plus or minus delta A and plus or minus delta B, whereas A and B are perfectly correlated, then you change the line into a square. Okay, take it to many dimensions, you see what's happening. So the short, I mean, this is a little bit of a long answer, but we're involved from, what did we actually learn from the signals and how we convert them into products, I would call it, that have, a minimum of correlation structures, nuisance parameters, and also designing information, and where we start designing experiment in order to extract information. And the beauty of, Yusuf has done quite a bit of work in optimal experimental design. The beauty of this setting is that the nuisance parameter, when it goes to an experimentalist, this is really instrument noise. I mean, if all you have is a yardstick, you're not going to measure the radius of the atom, right? I mean, but at least for certain quantities of interest, in the optimal experimental design, what features in the statement before you actually optimize it is, what are you going to measure it with, and to what precision do you think you can do that? Because depending on that, then the answer might change. And in some cases, we can say, don't bother measuring this, because if this is all the precision you take, and all the parameters are giving me variability that is less than the precision, at least for those conditions that are doable, we're not going to see it. So long, very important question, and it's at least to get the experimental group talking with the design and the simulation. What I said in a few minutes took 4 years till it became, till now it is routine. Yeah.
So kind of a mathematical question and a physical question. So it was interesting that in the if you just ran optimization using Hessians and adjoints, that it was more expensive than building a surrogate over
Yes.
the whole space. But as the dimension gets bigger, do you think that trade-off is going to flip? Because I mean, in optimization, you're exploring a very narrow region of the space-based principle.
The short answer is yes. I expect that as you go to very high dimensions, then the trade-offs are really not clear.
Then you wonder, so how do you put these together in some...
But I mean, the interesting thing is that what used to be 3 has become 30 and maybe 3,000 in the past 10 years. So in the sense that, you know, what I can do with, I mean, can you really infer 3,000 parameters if you only have 3 data points? Probably not. But if you have, you know, 3,000 parameters, then with, you know, at least on simple problems, if I do 30,000 runs, then I have a pretty decent emulator with, you know, sparse representation, with dimension reduction, with reduced spaces, with low rank, with lots of other, with likelihood informed spaces. So, but the short answer is on the mathematical side is yes. As the dimensions gets larger, it becomes more difficult to build surrogates. And then the variational approach, I mean, in the cases may actually go back to winning. Yeah. But at least in this example, I mean, I got the full surrogate even at a cost that is cheaper than finding the map.
Yeah.
Yep. And you had something on the physics.
On the physical side, this was about the repeatability of worth. I mean,
Yes.
The fact that I guess, I mean, there's so many instabilities in the dynamics that, I mean, in some sense, okay, they're triggered by how the MapReduces run and a particular sort of parallel configuration. But on the other hand, they're there because some intrinsic I mean, they're intrinsic to the system. So the fact that you're getting what seems annoying, like this lack of repeatability, it almost seems like that's something that physically is meaningful and that you'd want to characterize. It just happens to be triggered by computational noise, but
yes,
or am I overreading it? I mean,
yes, it's meaningful, and yes, it is a chaotic system. You know, I mean, if it wasn't that unstable, then why would the hurricane form in the first place? If you know, and if we really didn't have conditions that were, you know, favorable to instability and to its formation. With very high resolution and with systems that under some conditions can be very chaotic, this is going to be a fact of life. So yes, it has to do with the physics. It really is so annoying, though, when a tool by itself is really not repeatable. Because, I mean, it would have been really great if we were in a position to sample the seed of the stochastic backscatter and treat it as, you know, a tool that forces in a way that we could at least navigate. But if we cannot control that, then it's simply a bit unfortunate. Yeah.
Actually, I think in the future all atmospheric models are going to become stochastic, because there's a strong push towards essentially replacing the subgrid scale parameterization from sort of the large scale dictating the small scale to sort of looking at the small scale probabilistically and just drawing one sample from possible subgrid scales. And so they're not going to be repeated. And so you're seeing application where you're creating ensemble of ensembles, which is just astounding to me. And it would be really nice to be able to characterize this stochasticity in the same framework as polynomial chaos or something similar. But I don't think it's quite possible, because at every set number of time steps, you're triggering another stochastic.
So it's very high dimensional.
Yeah, very high dimensional. You have no hope.